Exponential growth and decay. Key concepts for exponential growth. Exponential growth can be modeled by the function y equals a times b to the x, where a is greater than 0 and b is greater than 1. The base b is the growth factor, which equals 1 plus the percent rate of change expressed as a decimal. Let's look at a problem. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about 360 billion was spent at restaurants. Part A. If the trend continues, about how much will be spent at a restaurant in 2015? We let y equals a times b to the x, which is an exponential function formula. Let x equals the number of years since 2005. Let y equals the annual amount spent at restaurants in billions of dollars. And we let a equal the initial amount spent in dollars, which is 360. And we let b equals the growth factor, which is 1 plus 0.07, which equals 1.07. So we write y equals 360 times 1.07 raised to the x, which is the annual spending in 2015. In 2015, since 2015 is 10 years from 2005, we substitute 10 for x and we get 360 times 1.07 raised to the 10th power. And our answer is approximately $708 billion will be spent at restaurants in the United States in 2015 if the trend continues. So now let's look at part B. What is an expression that represents the equivalent monthly increase of spending at US in the United States restaurants in 2005? For this part, you will need to find an expression of the form r raised to the m, where r is approximately the monthly growth factor and m is the number of months. So we have 1.07 raised to the x power, which represents the yearly increase, where x is the number of years. Then we fill in everything in for r and for m. We have 1.07 raised to the x equals 1.07 12 raised to the power of 12x over 12, um, since there are 12 x months in x years. Then we take that same result of 1.07 and we separate the fraction over 12x over 12 into 1 over 12 times 12 raised to the power of 12x, and then we simplify, which we get approximately 1.0057 raised to the 12x. Now we have 1.0057 to the m, and 12, we let 12x equals m, which is the number of months. So the expression 1.0057m represents the equivalent increase of spending at the restaurants. Okay, so now let's look at exponential growth as compound interest. Compound interest is an example of an exponential growth. It is when the banks pay interest on both the principal and the interest earned on an account. The formula for that compound interest is A equals P times the quantity of 1 plus R over N raised to the NT. which is also the formula to find the balance of an account that earns compound interest. And in this case, A is equal to the balance, P is the principal, R is the annual interest rate, and N is the number of times the interest is compounded per year, and with T being the time in years. So let's look at this example. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So we make it a table and we have what we know, what we need, and what we plan. We know that we have $2,000 for the principal, 4.5% interest, and the interest is in compounded quarterly. We want to know the account balance in 18 years, and the plan is for us to use the compound interest formula. So we have A equals P times the quantity of 1 plus R over N raised to the NT, which equals 2000 times 1 plus 0.45 divided by 4 raised to the 4 times 18. And we're substituting the values for P, R, N, and T respectively in this equation. So therefore we have 2000 times 1.01125 raised to the 72. And simplifying that, we get the balance to be 44,475.53 after 18 years. So now we're looking at exponential decay. The function y equals a b raised to the x can model exponential decay as well as an exponential growth. In the exponential decay model, a is greater than 0 and 0 is less than b and b is less than 1. The base is the decay factor, which equals 1 minus the percent rate of change expressed as a decimal. Here we have a still being our initial point amount when x is equal to 0, and we have the base b is the decay factor in this particular problem instead of the growth factor. So we have a problem that involves exponential decay. The kilopascal is a unit measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals for every 1,000 meters. Increase in altitude, the pressure decreased about 11.5%. What is the approximate pressure at the altitude of 3,000 meters? Remember, we're using the functional expression y equals a times b to the x, and we're letting x be the altitude in thousands of meters, and y be the atmospheric pressure in kilopascals, and we let b be the decay factor, which is 1 minus 0.115, which equals 0.885. Since we know that y equals a times b to the x, a equals 101 and b equals 0.885, then we substitute them in the exponential function equation. So we have y equals 101 times 0.885 raised to the x. Well, we know that x is 3, so we substitute 3 in for x, and we get approximately 70 kilopascals. So the pressure at an altitude of 3,000 meters is about 70 kilopascals.